Above this 450-meter abyss stands a structure that appears to defy gravity.
The valley is too deep for ordinary bridge foundations or conventional construction access.
Today, we reveal how engineers built this terrifying pathway above the abyss.
Wind, fractured rock, falling debris, and isolation threatened every stage of construction. Subscribe as we follow every hidden anchor, from survey to final operation. No usable road reached the locations where the main structure had to stand. The solution would combine cliff anchors, cantilevers, columns, and radial steel framing. Every visitor adds bending, tension, compression, and vibration to the supporting system. Full-height piers from the valley floor would be financially and technically unrealistic.
Could scattered rock pinnacles become foundations for a transparent pathway through open space?
Existing viewpoints could not safely accommodate the region's growing visitor numbers.
The most dramatic canyon views remained beyond the edge of accessible ground.
A landmark attraction could support local transportation, hospitality, guiding, and maintenance jobs.
The structure required strength, transparency, controlled movement, and dependable evacuation capacity. Timed admission would prevent dangerous crowd concentration on the transparent observation deck. A circular platform would distribute visitors while providing an uninterrupted panoramic experience. Every exposed component needed to survive rain, temperature change, and mountain wind.
Individual panels had to remain replaceable without dismantling the surrounding walkway.
Measurable performance limits transformed the attraction into a controlled engineering project. Before designing foundations, the team needed an exact map of the mountain. Satellite data established the canyon geometry before field teams approached the cliffs.
Drone photogrammetry converted overlapping photographs into an accurate three-dimensional surface model.
Rope teams inspected fractures that remote imaging could not evaluate closely.
Permanent control points fixed the position of every future column and girder. Core drilling revealed rock strength beneath the fractured and weathered outer surface. Compression tests measured how much concentrated structural force the limestone could resist. Fracture mapping identified natural planes where concentrated loads could separate the rock. Several boreholes exposed hidden voids created by water dissolving the limestone.
A dedicated weather station recorded gust speed, direction, turbulence, and temperature.
Moisture testing showed how quickly wet transparent surfaces could lose safe traction.
All geological, topographic, and weather data merged inside one coordinated digital twin.
Strong foundation rock existed, but it was scattered between weak and hollow zones.
The highest bending forces accumulated where the elevated walkway entered the mountain. A foundation misplaced by centimeters could enter fractured rock or an unseen cavity.
Using existing rock pinnacles avoided impossible foundations at the distant valley floor. Full-size girders could not pass through the narrow and sharply turning mountain route. Mountain gusts could twist the deck and generate uncomfortable structural vibration. Daily temperature changes would repeatedly expand and contract the exposed steel structure.
The transparent floor had to resist sudden localized impact without complete failure.
Crowd footsteps could amplify movement if their rhythm matched a structural frequency. Poor drainage could leave standing water on the glass and around steel connections.
Workers required rapid rescue access beneath every incomplete and exposed structural segment.
One concealed foundation defect could affect columns, girders, connections, and glass.
The final system had to distribute forces across several independent foundation zones.
5 structural approaches were compared for stability, access, cost, and constructability. Engineers selected a hybrid system, combining anchored cantilevers and pinnacle-supported columns.
Upper anchors resisted pullout, while lower struts transferred compression into the mountain.
Tubular columns transferred vertical loads into reinforced foundations on stable rock pinnacles.
Radial beams spread platform loads between the central hub and perimeter ring.
Bonded tempered layers retained strength even after one glass layer became damaged. Elastomeric pads distributed pressure and prevented direct glass contact with steel.
Expansion joints absorbed thermal movement without loading the brittle glass edges.
A multi-layer coating system protected exposed steel against moisture and corrosion.
Pressure relief openings reduced uplift by allowing turbulent air to escape beneath the deck.
Modular construction reduced lifting weight and shortened dangerous assembly work above the canyon.
Construction began only after every load path, connection, and safety system was verified.
Crews created limited access for personnel, cables, compressors, and compact machinery.
Natural ledges were stabilized before supporting temporary equipment and material platforms. Ropeway towers required independent foundations beyond the permanent skywalk alignment.
Light pilot ropes gradually pulled stronger lifting cables across the inaccessible canyon.
The completed cable crane became the project's airborne transportation system. Suspended scaffolds provided stable access beneath every developing structural connection. Independent lifelines protected workers if temporary scaffolding or equipment unexpectedly moved. Ryan approved every worker's fall protection equipment before cliff access was permitted. Temporary power-supplied drilling, welding, lifting, lighting, and monitoring equipment. Strict staging prevented stored materials from overloading the narrow mountain platforms. A complete rescue drill verified response capability before construction extended outward. Every steel plate arrived with certified strength and chemical composition records.
Computer-controlled cutting produced complex profiles with repeatable millimeter-level accuracy.
Hydraulic forming created the precise curvature required by the circular platform. Jack verified the first girder before authorizing repeated production of identical modules. Ultrasonic inspection revealed internal cracks and incomplete fusion hidden inside welds.
Subscribe as these tested components leave the factory for the mountain.
Shot blasting removed scale and created the texture required for protective coatings.
Each protective layer was measured before the next coating could be applied.
The ground mock-up exposed connection conflicts before assembly moved above the canyon.
Ground testing confirmed that physical steel behaved like the structural calculations predicted.
Thermal tempering strengthened each sheet by creating permanent compression at its surface. Heat and pressure bonded separate sheets into one load-sharing laminated panel.
Panels with microscopic edge damage were rejected before leaving the factory.
Components arrived in installation order to minimize handling at the confined mountain site.
The first major lift delivered foundation equipment to an isolated rock pinnacle.
Cole aligned the drilling rig with coordinates transferred from the digital model.
Each borehole followed a designed angle toward competent rock beneath the surface.
Continuous extraction prevented loose dust from concealing changes inside the borehole.
Every completed hole was scanned before engineers permitted permanent anchor installation. Thorough cleaning allowed structural grout to bond directly with sound limestone. Centralizers maintained uniform grout thickness around every high-strength steel anchor. Bottom-up grouting expelled trapped air and filled irregular spaces around the anchor.
Anchors remained unloaded until the grout achieved its specified structural strength.
Every permanent anchor carried a verified test load above normal service demand.
The first tubular column descended onto a foundation isolated high above the canyon.
Leveling hardware positioned the column before permanent bolts were tensioned.
Balanced weld sequencing prevented heat distortion from misaligning the tall support column.
Every circumferential weld passed inspection before the column accepted structural load.
Synchronized guidelines stabilized the first main girder during its canyon crossing.
Temporary pins fixed alignment before calibrated bolts created the permanent connection.
Each completed span created access and support for the following structural module. Radial beams linked the reinforced central hub with the platform's perimeter ring.
Independent vacuum circuits protected each panel if one suction system failed.
Measured spacers preserved expansion, drainage, and flexible sealing gaps around the glass.
After months of controlled progress, the transparent structure approached physical completion. A sudden mountain gust exceeded the approved limit during a glass lift.
The wide panel acted like a sail and began rotating toward steel. Ryan stopped every lifting operation and cleared personnel from the danger zone.
Controlled winches secured the panel before it could strike the completed structure.
Hours later, 2 newly installed foundation anchors failed their proof tests.
Both anchors crossed a hidden cavity beyond the original investigation holes. Continuing construction would overload neighboring anchors and compromise the column foundation. The foundation zone was isolated before additional structural weight could be added. The shutdown protected workers but increased exposure, storage, and schedule risks. The project now faced unstable lifting conditions and unreliable foundation rock. Laser comparison confirmed the surrounding rock mass had not physically shifted. Additional probes defined the cavity's full depth, width, and connection paths. Engineers redirected longer anchors around the void into deeper competent limestone.
Real-time drilling data verified stronger rock before each hole reached final depth.
Controlled pressure grouting filled the void without fracturing surrounding sound limestone. Additional anchors spread column reactions across a larger volume of reliable rock.
Placement anchors exceeded required resistance, with almost no permanent movement.
Future lifts required a verified low-wind window through the entire operation. Dual guide winches prevented rotation, while the main cable controlled vertical movement. Verified foundations and controlled lifting allowed construction to resume safely. Hidden conduits supplied sensors, lighting, communications, and the monitoring network. Strain gauges measured how forces changed through anchors, columns, and girders.
Local weather instruments triggered restrictions before wind reached unsafe operating levels.
Precision lasers tracked vertical and lateral movement to fractions of a millimeter. Operators could evaluate the entire structure through one integrated digital dashboard.
Sloped channels carried rain and condensation away from glass and foundation connections.
Transparent barriers preserved visibility while resisting crowd and emergency impact loads.
Independent backup systems maintained communication during power loss or sudden closure.
Transparent surface treatment improved wet traction without blocking the canyon view.
Every structural, electrical, drainage, monitoring, and safety system was checked together. Static proof loads simulated maximum approved crowds across several occupancy zones. Measured deflection remained within the narrow tolerance predicted by the structural model. Dynamic testing confirmed walking rhythms would not create uncomfortable resonant vibration. Wind trials verified deck pressure relief and transparent barrier resistance. Impact testing damaged one layer while the bonded panel continued carrying load. Localized testing verified that edge supports distributed, concentrated loads without damage.
Rain testing confirmed rapid drainage and safe traction across the treated glass.
The evacuation drill cleared every visitor zone within the approved time.
Sensor results matched calculations across foundations, steel, glass, and safety systems. With every requirement satisfied, the Skywalk received authorization for public operation.
Subscribe and join the first visitors entering the completed glass Skywalk. For the first time, ordinary visitors stepped directly above the immense canyon.
The transparent floor produced intense fear while the structure remained safely controlled. Operators continuously watched the forces visitors could never see beneath their feet.
The project transformed a remote cliff into a carefully managed tourism destination.
Visitors see glass above an abyss. Engineers see foundations hidden inside stone.